So today we're going to talk about two things, line and surface integral and the theorems on lines and surface integral and application. So if you have time, we can finish it today or we can do the next week what is left. So I'm going to review the same thing again, but in different settings. Of course, it's written in the nice LaTeX form, but also you might see that there's some difference between what I just said in the board in the previous classes. So what is the line integration? So line integral, there are two. One is line integral of real valued function, which is it here. And there is a line integration of vector valued function. So let's talk about this first. So line integration is basically integration on a curve. The line means the curve. Line is one-dimensional. Curve is one-dimensional. So let's say we have a parameterization of a curve. So I decided to use different symbol for the parameterization, which is a function as a small c. And the curve itself could be written as the large c to indicate it is a set of points in n-dimensional space Rn, and there's a typo, sorry, so c dots. So let's say we have a function of n variables, which has a real value. So it's defined on C. So even if it has an n variable, it doesn't mean that it always defined at every point on the Rn. So the reason why we have n variable is because only way we can identify point on a curve is using this n variable, because the curve itself is in the Rn. And let's say we have a partition. So what is partition? Here, you can see my book about the definition of partition. So partition is just increasing finite sequence of points from the left end to the right end of the interval given in the parameterization. So T0 is A, Tn is B, and there are n subdivisions. So therefore, as a total, we have n plus 1 point to partition this entire interval. And you can have assumption that this partition is equally spaced partition, so which means that Ti and Ti plus 1 is always the same amount. And we have, let's say, a point at each point Ti. So let's say T is the time parameter, then Ti, you're at the Ci point. And what is this line integration? So this is just a symbol indicating a number. And what is number? How does number computed? It's computed by the limit of something, limit of a formula in terms of n. So there's only one parameter in this formula, the big sum, which is not determined, which is n. The number of subdivisions can be changed. Other than that, everything is fixed. So the partition is fixed, function is fixed, the parameterization of curve is fixed. So everything can be computed without knowing anything. Just with all the information is given except the number of partition. So you compute the value of function at the point Ti star. So Ti star is a random point, any point in between the interval, sub-interval from Ti to Ti plus 1. Here Ti minus 1 to Ti. And then you compute your point. You compute the coordinates of the point at Ti star on the curve, and then you put that coordinates into your function to get the value of function at that point. And then you're not summing up the value, you're multiplying the value with the length of a small line segment. So what is this? So we have 2 points, Ci minus 1 and Ci. It's a starting point and end points of the vector. So if you take a vector, so that's why I put the arrow above here, and then you take the norm, that means it's the length of line segment joining the 2 points, Ci minus 1 to Ci. So basically you compute the value of function with the length element, and if you take the value of function to be the height, then it's basically area, the small areas on top of the small line segment of the curve, and you sum them up for entire subdivisions. There are n subdivisions, you sum them all together to get approximate area under the curve. So here's the picture. So here's an example. Here's the picture of the situation. You have CT and you have a curve above that CT line, and then you take in the small sum of small areas, and if you get the numbers to be the number of subinterval to be infinite, then your error gets smaller and smaller. So basically you get the exact area under the curve. So that's the meaning of the line integral. So you can think of this in a more general settings. So for example, if you have a smooth curve, then you can always parameterize with one formula, let's say sine, cosine, whatever, polynomial. But you might have a curve which has a sharp corner, which can be, which cannot be expressed by one single formula, or sometimes your curve could be disconnected each other. So one curve here, one curve there. And the line integral actually doesn't say anything about the condition of curve. As long as it can be parameterized by some function, that's fine. So you can chop, in that case, if your curve is not smooth at some point or some finite points, or if your curve consists of lots of distinct elements, like disconnected parts, then you can integrate the line integral on each curve and then sum them up to say this entire sum is the line integral of the function over this entire curve pieces. So that's what it says. So basically you can chop them up into pieces. All right, so example here. So let me skip the example and go back to example after we finish, because I need to use the board. So let me just give you one example here. Just think about how you could tackle this question. So I have a curve from O, P, P to Q, Q to R. So it consists of three line segments. So each line segment is very smooth. It's a straight line, but the connected point, these points are very sharp corner. So you can, and also you cannot say in one single formula how this curve is defined, right? You have to split, you have to use three formulas to parameterize this part and this part and these parts. So basically what you need is to integrate over OP and then P to Q and then P to R and then sum them up to get the line integral. And you see here, this is our formula. This is our function in terms of 3 dimensions, because the curve is in 3-dimensional space. And we have just the usual formula here over C and ds part. And if you understand this, so think about ds. So ds is always, what does ds means? ds is the length of small line segment that you chop them up into small pieces and then you want to approximate the small length. That's ds. So when you integrate over OP, ds, so here I didn't mention this axis. So this axis is x, this is x, this is y, and that's z here. And your x-axis is increasing in OP line. OP line segment, y and z is not changing. So dy, dz is 0. So ds is basically the length of that segment, which is equal to ds. The x. So on OP line, what you're integrating is the x plus y plus z dx, right? Where y and z considered to be constant. So just as we had it done similar in the line integration in vector fields. And how about PQ part? In PQ, your z is changing. It's the only thing that changes. X and y is not changing. So x is changing means the ds is dz, right? On PQ part, ds equals to dz. So you can just compute the line integral as a single variable integration, considering x and y to be constant. Actually, it's constant when x is 1 and y is 0, right? And z is changing. So we'll get there after we finish it. So let's now move on to the vector fields. We want to talk about the line integration of vector field. So what is the vector field? It's a function that maps vectors to point. And the dimension of vector and the dimension of point must be equal. So it's if you just write it as a functional notation, it's just Rn to Rn. But here, the domain Rn is the point, the codomain is the vector. So they are different in nature. And we already talked about this, but let's review. And we call this as a nabla operator. And using this nabla operator, we can define divergence and curl. So curl is defined to be the operation to the vector field on three-dimensional vector field. And if your three-dimensional vector field has PQR coordinate function, then the curl has these coordinates. I said that this is complicated. If you try to remember it by the symbol, you will always confused. So just try to remember it as a determinant of 3x3 matrix. And also you can define the divergence as the following. So the nature is different. The curl is the vector field. You see there are three coordinates. But divergence is the value. Okay? So divergence gives the value. So PQR, when you take the partial derivative, it's still a function. So both are taking x, y, z as a coordinate, as an input, but the output is different. The divergence is a value. Divergence gives you value, but curl gives you vectors. And in terms of divergence, if you talk about divergence, you can also define divergence of the two-dimensional vector fields with the assumption that your operator has no third coordinates here. All right, so this is what I just said. So remember this picture, okay? So your nabla considered to be a vector. So your nabla, but it's not really a vector because the coordinate is not a number, but just put the operator. So nabla consists of operator. All the coordinates are actually operators. So put the operator on the place where it should be when you take the cross product of two vectors, and then these are here, and put the coordinates of f, PQR on the place where it should be when you take the cross product, and then the top row is basically has to be fixed. So it could be written as ijk or e1, e2, e3, meaning the three standard bases of three-dimensional vectors. And you just take the determinant, and you will see that the e1 is multiplied with this one, and minus this one. So when you multiply the operator with the function, it means that you're acting your operator on the function. So it's not multiplying the operator to r, it's actually combining operator and function to get another function, where in this case r partial derivative by y and q partial derivative by z, and so on. And also here, when you take the divergence, sometimes you put a dot, the small dot for divergence, because it's evident when what you're saying. So if it's not a cross, then it has to be dot. And if you take a dot between this operator and the three-dimensional vector field, then what other operation you can do except for the inner product, because you cannot multiply two vectors. The multiplying two vector, you always refer to as inner product. So we took an inner product here, and explicitly here we expressed as the inner product symbol. So we have a p acting on, so this operator acting on p as if it's just multiplying these two, but it's not really a multiplying. So, and then we get the px. So it's just the way of defining this curl and divergence. I'm not saying this is what it should be. I mean, just the way of remembering the rule or definition of curl and divergence, because it's easy. Just take this as you can take this as a definition if you want to. So so for someone who actually, so I'm recording this video in a screen mode, and also I'll upload this PDF file on my Notion page. So don't worry about going too fast. Just keep up with me to understand what I'm saying. And if you have any questions, let me know anytime. Just stop me anytime. Okay, so another thing that we can do with the nabla operator is putting the nabla operator on the function, not a vector field. So far, this nabla operator is acting on the vector field here. The bold one is a vector field. Okay, you can either take the curl or divergence, but if you take acting your nabla operator on regular function, which is real valued function, you do exactly what you do as a scalar product. So it's something like f serves as a scalar product. So you take a distribution rule to put f on every coordinate here. So it was just the nabla operator. It's just a partial derivative operator, but you put the f to get the del f, del x, del f, del y, del f, del z. So every coordinate becomes now a function, just real valued function. So what does this mean? You can take x, y, z as an input and then plug that in each coordinate function, and you get the value for each coordinate. So basically you have x, y, z as the input, and then you get three-dimensional function, three-dimensional vector. So it's a vector field. So when you take a nabla operator acting on a regular real valued function, you get a vector field, and it's called a gradient vector field. So it's a gradient basically, right? So this vector is the gradient. That's why it's called the gradient vector field. And there's a lot of formula, and I don't say you have to memorize this. If you want to, you can easily derive the inequality here. And some equality is not intuitively clear, but these are something we need mostly in the part where we deal with the physical equations, like I just forgot the electromagnetic fields or something like that. So let's talk about these two things. We have a gradient vector field. Okay, so whenever it's not bold, it means it's a real valued function. If it's bold, then it's a vector field. So this just regular f and bold f is not related at all. It's just two different things. So this is just regular. It means any regular real valued function. This means any vector field. So let's say we have a gradient vector field and then take the cross product with the Nobel operator, which means that we take the curl. What does that mean? I mean, and then the first equation said it's 0. So 0 here is boldface 0, meaning that it's not just scalar 0 or real value function 0. It's a 0 vector field. That means every vector that assigned to point is always a 0 vector. So it says that gradient vector field has no curl. You can say this equation in words like the gradient vector field has no curl. So what does it mean that you have no curl? So no curl means that if you think vector field that you take for the curl is giving you some way, giving you some idea how the materials or flow or liquid is flowing on a space, then no curl means that the vector field is not rotating at anything at any point, right? There's no work that actually enables to rotate object around any point. And on the second equation, it says that if you take the curl and divergence, so this is divergence, right? So when you take the curl, you get the vector field, and you can take the divergence after that. It means 0. So you can say that the curl vector has no divergence. What does that mean? So no divergence means that it's not expanding at any point. The divergence, basically the word itself literally means that it's expanding, right? So no divergence means it's not expanding, and it says that the curl vector, whatever the original vector f is, the curl vector is not expanding, okay? Well, you can think about this as a physical situation also in electromagnetic fields. There are meanings to this, but let's leave it later. And all the other parts are somewhat tedious or somewhat obvious. So in the third and fourth, it's just the distribution rule of the inner product and the cross product, basically. And these parts follow from the product rule of the derivative. And this is more complicated, but you can make it a direct meaning geometrically, but it's not clear. I mean, it's not simple. So the 5 to 8, you don't have to memorize. I mean, if you really need to, we can make it use whenever we need by looking at the formula. So we're not going to use this 4 last formula until we get to the physical application. So anyway, all right. So we are still on the line integration business. We actually take a different route here. So anyway, the vector field. So we want to take the line integration of vector field. What is it? The definition is so this is just notation. So we have a dot, which means the inner product and the vector field. And the ds part, the s, is now written as the vector form. What do you mean by that? The s is vector form, because we don't want to lose the information of vector. So vector consists of length and the direction. So the line integration of the real valued function has ds, which only have the length element, no direction, okay? But in here, we want to keep the direction element. So here, the definition, look at the definition. Everything is same except we have c prime instead of c prime absolute value. So absolute value, whenever you put the bar around this, you get the length of the vector. But you don't take the length. You get the vector itself, and then take the inner product with the vector field. So there are two things. So one thing is the orientation of a curve, orientation of parameterization of this curve matters whenever you compute the line integration of vector field. And also the meaning is different. The second thing I want to emphasize is that the meaning is different. In the original line integration of real valued function, you can say it's the area under the curve, whatever. But here, it's not about area, okay? So you have to make a meaning of the inner product. So the easiest way in the physical sense to get the meaning for the inner product is the force. All right? So you want to think about the force acting on the direction of your movement or tangential movement of your point on the curve. So you want to compute exactly the amount of force that actually moves the point along the curve. So there are two components of force on every part of the point when the point is moving. So the one is the tangential direction and the other is orthogonal direction. So the orthogonal direction is not actually doing anything on the movement, right? Because the point is moving along the curve. So whenever you take some pushing in something, if it's not moving in that direction, you're not actually doing that work, right? So there are always the counter force, but it's not actually work. So you only take the part where it's tangential to the movement, and also you take the inner product, which means of the vector itself, which means that you want to measure the exact amount of movement. You want to keep the length element too. So if you take the component of your force, which is tangential, and that's a force, and multiply that with the length, that's the work, right? Force times length is work. So you're taking a work and then integrating the work, which means summing up all the work that you did to the point along this curve, where the t from A to B. So if the point is moving from this point to that point, you're doing some work. But if you're considering the same situation in an opposite perspective, that your point is moving from here to here, then the same vector field must have to do the negative work done, or have to do the negative work to the original work that the vector field must have done to move the point from here to here. So if you change the orientation, which means that if you change the starting point and end points, then the total work that the vector field has done is negative to the total work that is done the opposite direction. So that's the only thing. If you change the orientation, you'll change the sign. The example here. All right, so that's what I just said here. The line integration of vector field depends on the orientation of curve. So not the absolute value is dependent on the orientation. It's just the sign. Okay, so actually the absolute value of the work done by the vector field may depend on the route. They may depend on the shape of a curve. But if you keep the same shape but changes the orientation, then your line integration will change the sign. Definitely changes the sign. All right, so the meaning of the line integration of vector field is the line integration of vector field of f, the integrand, along a curve is the work done by the vector field, or you can say it's a force field, f on the particular movement along the C. The particular movement is particle or moving is inevitably have orientation, right? You cannot say, I don't know. You always have to have certain orientation of the movement of a point on the curve. Okay, so that's already implied here. And also example here. Okay, so here I also mentioned that there are a lot of different ways of writing the line integration. This is one of the common and useful way of writing it. And if you do this, you can make an example of this, and I'll just do it, keep it going here. From here, let's talk about this more. So we say a real valued function is potential function for a vector field f. So here, a small f and the boldface f is totally unrelated. So just give two different function and the vector field. And they are related if the vector field is the gradient vector field of the given real valued function. And we say this real valued function is potential function of that vector field. Again, let's say you have a real valued function and vector valued function. Okay, totally two different things. But if it happens to be that if you take the gradient vector field of the real valued function and it's exactly same as the given vector field, then you can say these two objects are related by saying that real valued function is potential function of that vector field. So I'll give you the example. Maybe I have an example later. Let's see. Yeah, so here, so look at this one. This two variable function on xy. So you can say two variable function, three variable function, as long as you want. Whatever. So let's say we have a two variable function in two-dimensional space, and this is inverse tangent function over y over x. Okay. So this is actually the potential function to this gradient vector field. So this vector field. So what is this vector field? Where is the vector field? So this is notation of line integration of vector field in a different notation. So instead of writing ds, I could write dx and dy, meaning that this part, whatever multiplied on dx, is the x coordinate of vector field, and this is the y coordinate of vector field. So we are talking about two-dimensional vector field. Minus y over this, x over this, and this vector field is actually given by the gradient vector field of these two variable function. So how do you check this? So you just compute the gradient vector field of f by taking the partial derivative of x of this function and y, and then see that x, and then you check that whether that's the x and y coordinate of the vector field I just showed you. Okay, so there are lots of exercise actually. So that's yeah, that's basically the part that I wanted to talk about, this 8.1. So I went very fast, and I actually the reason why I didn't want to use the presentation is because I could do this, and I'm sure that you guys have lots of questions. So let me take a question and then go back to the question few examples. I cannot go through all of them, but I'll go through the important ones. Any questions? Yes.
But not related to presentation.
Which one?
About like I prepared with a book and I have one.
Oh yes. Okay.
Can you look at my notes? What is the difference between when we have function, for
Yes.
example, and we take like we have dz.
Yes.
But in this case, we have ds.
Okay, so let's go back to this example here. So let's say C1 is OP and C2 is PQ and C3 is QR. Okay? So if you want to integrate that function, that's a function, right? So you can split this integration into three pieces. So let's take the first one. So integration on C1 is basically you have a function and ds. That's the definition, just notation. And what is the function? It's x plus y plus z, real valued function, and C1, and still ds. But now think about what ds is. ds is the small line segment changing that position, the length of the 2 points changing its position as it moves along this curve. So the point is moving along this not wiggling curve. It's a straight line along this x-axis. So this is x-axis, y-axis, z-axis. So ds is basically same as dx. So originally ds is somehow, let's say if you really want to talk about how much it actually moves, you have to use Pythagorean equation that it's the square root of square sum of the movement in x, y, z, right? But there's no y and z movement. So del y, del z is 0. So basically in this case, ds is equal to dx, right? So let's still write this as the x, but everything is same. But now your only parameter that changes the position, changes the coordinate of the point is x. Okay? So you still want to move your point from 0 to p. So again, this one, it could be p to 0 because it's just the integration of real valued function, but we say that it's moving from o to p. So how do you make your coordinate change from 0 to o to p? By changing the parameter x. So you're saying that when you move x, y, z along this OP, y and z are fixed. So if you move along this point, this line, your y coordinate is fixed as 0, and your z coordinate is also fixed as 0. Your y, z is always fixed as 0, but your x is changing its coordinate from 0 to 1. So it's changing from 0 to 1. So it's just as if I just replace my C1 as an interval 0 to 1, and then take this left and right limit as my limit of integration, and x, y, z, dx, and also yz is 0. I can just eliminate this. So basically it's integration of x. We know how to do this, right? Just the usual integration, and 1 over 2x squared, 0, 1, 1 over 2. So integration on C1 is 1 over 2, and you can do this for C2 and C3, just the same way we did. So that's what you're talking about, just why we can do this. So for example, let's talk about C2. How do you integrate C2? So C2, so let's skip all the middle parts, is determined by the z-coordinate, and x and y coordinates are the same. X is 1, y stays as 1, 0. So z is only changing. So here x is 1, y is 0, and z is changing from 0 to 1 if you want to move it from P to Q. And the coordinate is, the value of function is x plus y plus z. X plus y is 1, so it's 1 plus z and dz. Okay, so now ds becomes dz. So it's 1 plus 1 over 2, it's 3 over 2. So you can do the C3 here, and then combine them together to get the line integration. All right, so that's the first example we had. What is, so let C be the line joining 0, 0 to 1, 2. It's a straight line. Find the line integration, 2x plus y. So this is, of course, first, whenever you take the line integration, decide whether you're going to take the line integration of real valued function or vector valued function. It's a real valued function, right? So we don't need to think about the vector or tangent vector of the movement, but still we need to parameterize the curve. So let's say, what's the easiest way to parameterize this curve? From origin to where? 1, 2? 1, 2? Yes, 1, 2. 1, 2 is about here. I want to go straight from here, 0 to 1, 2. So then it's easy to parameterize by x coordinate. Let's say this is my t, and this is my, so let's say this is x, and this is y. So anywhere in between 0 to 1, there is a parameter t that moves and in the direction, in the speed of 1. And every point here is t comma 2t, right? Whenever I have a parameter t and x coordinate, and my coordinate of point is t comma t. And ct is t to t. And what is c prime t? It's vector 1 comma 2. So what is the length of this vector? It's square root of 5. So how do we compute the line integration then? So first write the integration symbol, c f ds. Not a vector, it's just the real number. And this is, so there are two ways you can do this. So you can just go for the limit, and that's the definition, but we don't always go for the limit because we know how to compute. So we have the parameter t, 0 to 1, is making this point moving along this line segment. And then we take f, c, t, and then multiply to what? The length of the tangent line, tangent vector, which is square root of 5 dt. So here, what is f? F is 2x plus y. So we want to plug in t for x and 2t for y. So it's 2t plus 2t, 2x plus y, right? And then square root of 5 dt from 0 to 1, because basically you have integration 0, 1, 4t dt. And now you can do this. Okay. Any questions? No? Let's do more. So we have another line integration of real valued function. The real valued function, the formula is x squared times y squared. And the curve is not straight line. It's the boundary of unit circle centered at 0, 0. So first we need to parameterize our circle. The easiest way of parameterizing the circle is using cosine and sine, right? So let's say we have, but now you have to decide which point you're going to take as a starting point. So if you take cosine t, comma sine t, and if you assume that t is running from 0 to 2 pi, then you're assuming the point is starting at 1.0, 1 comma 0, and then moving in the counterclockwise. Okay, but let's say this is c1t. But there's another parameterization. So I want to show you what happens when I choose different parameterization of the same curve. So let's say we have a sine t and cosine t, but let's say t is from 0 to 2 pi. Where is the starting point? So when t equals to 0, it's 0, 1, so it's on top. And in what direction were these point moving in C2 parameterization? Counterclockwise or clockwise? Clockwise? Yes, right. So we have x is increasing to positive, so we have a clockwise movement here. So let's compute in two different parameterization and see what the results are. So first, C1 parameterization, what is it? C1, and we have 0 to pi of x squared sine y squared, so it's cosine square sine square. And now we have to multiply what? The length of the vector, length of C prime, length of C1 prime. The C1 prime is minus sine comma cosine. And if you take the length, it's always 1. So you don't need to multiply anything here. So that's the result. And what about if you take the C2 parameterization? Your integration, the bound is same because t is running the same range. And we have x as a sine, y as a cosine, which is also squared. So sine square, cosine square. And even if you have different parameterization, this one, if you take the velocity vector and take the norm, it's always 1. So it's just the same thing here. You get the same thing, right? So you might say, oh, wait, okay, so this might be just coincidence because we have x squared and y squared. What if we have a different symbol? Well, it's just actually same. I mean, I don't want to prove you by giving you lots of examples. I mean, you can get assurance that the result will be always the same. But let me give another example. So let's say we have C3t, and we're gonna use the same formula, cosine t. But instead, let's say I wanna take the t to be not from 0 to 2 pi, I'm gonna run the 0 to pi. Okay, so then I'm making a half circle, right? But in this example, C must be the full circle boundary. So in order to make up the last half, then I need to go twice faster than previous. So not t, let's say 2t. Okay? So then I can make a full circle, but the t is now ranging in different. And this C3 is completely different story. So it's moving in the same curve, but the speed is different. Okay? So let's see what happens when I use C3. So I get the same formula when I plug in x and y, but now I have a different range. Now it's up to pi. And now I have to be careful about when I'm multiplying this. So what I have to multiply, which I didn't write here explicitly, is that I need to multiply the length of the vector, the norm of the vector. So here the C1 prime t was 1. What is C3 prime t? So here I take C3 prime t. It's, don't forget 2t here. So it's minus 2 sine 2t, comma 2 cosine 2t, right? So therefore, C3 prime t has the norm equal to 2. So I need to multiply 2 here. Okay, so that now you get this different formula. So I get the same integrand, but because there is a difference in the bounds here, and there is a difference in the factor, so I really need to compute the final answer in order to see that they are the same. But they are the same, so you just check this out. Okay? And we can prove it, but well, if you get the assurance by working on with this specific example, then I'm sure you don't want to. I mean, you don't need to look at the proof. Proof is just mathematical rigorosity. It's not necessary here today. All right, so let's look at another one. So we have, this is about the 3-dimension. Let's skip this. And let's go to the vector field part. Let's do this one. So find the following line integration along the curve shown at the right. Okay, so here we have vector fields, and we have a closed loop consists of 4 different parts of the line segment L1 to L4. Let's compute this. Any questions about this before I move on? Okay. So let's see. That's again. I want to take the line integration on each pieces and then sum them up. So in the line integration of vector field, you have to think about orientation. So when you take the line integration on L1, the point is moving from here to here. So don't forget that. So let's write the formal notation and then use this notation later. So here it's minus y, x squared plus y squared, and x squared plus y squared. That's your vector field. And then ds. Okay? That's what I want along L1. You still want to parameterize your curve. It's always what you need to do. So in this case, L1 is L1 is changing its position from, what is it? 1, 1 to minus 1, 1. So the y coordinate is always the same. So let's say C1. Let's call parameterization C1t. So y coordinate is always 1. But your x coordinate is changing. That's just t. So x coordinate is the same thing, right? So x coordinate is 1, and y coordinate is changing its coordinates. Let's call t to be the y coordinate. Then I want the t to change from 1 to minus 1. So this is the starting and this is the end. So if I use this, then the starting goes to the bottom and end goes to the top, because that's what I want. That's the orientation I want. And then look at this. So minus y x y dx plus x dy. But dx is 0 because it's not moving in any x direction. So I can just eliminate all this. And what about x and y? So it's now parameterized as 1 and x, or 1 and t. So it's 1 over 1 plus t squared, right? Y is t. And then what is dy? Y is t. So therefore, dy equals dt. So I want to find, so this is just single variable function integration, definite integration. I want to find the antiderivative of 1 over 1 plus t squared. That is the arctangent. Okay? So that's the antiderivative. If you take the derivative of arctangent t, then you get this. And what is the limit? So it's changing from 1 to minus 1. 1 to minus 1. 1 to minus 1. So therefore, I need to take the tangent inverse of minus 1 minus tangent inverse 1. So what is tangent inverse of minus 1? Minus 4. What, 4? Pi over 4. And pi over 4. So it's minus pi over 2. So you can do the same thing, similar thing for other parts. And if you do this, you will see that it actually becomes 0. And let's try this. Okay, so let's try this example. So we have another vector field, x squared comma y squared. And there are two so that the picture has to be different. Yeah, but the picture is nothing to do with the exercise. I put the picture as a helping picture that I want to explain through this example. So the picture on the right hand side must be the picture that splits the circle in the two parts on the left and right. So on the left we have a split of the circle in top and bottom. I should have put it on the left and right split, but let's just ignore the picture. So just think about the example formula here. So it says that I parameterize. I want to move my point along the boundary of a circle, unit circle, counterclockwise. So I need to parameterize that way. So we have ct equals to cosine t and sine t. And if you want to, so that's basically the counterclockwise orientation. If you take the t from 0 to 2 pi. So I'm going to give you two different ways of computing this. So for example, the formula says that this is our line integration. The vector field is here, and this is what our notation. And you can also write that out as this, y squared dy. So when you write this way, then usually it's by notation, what it says is x is now cosine t and y is now sine t, and ds part becomes c prime t, and then you just either take the inner product and c, and this integration over c becomes the t is moving from 0 to 2 pi, so t is from 0 to 2 pi, and cosine squared t, sine squared t, that's your the tangent, the vector field at every point t. And then in the product with the c prime, which is minus sine t, cosine t, dt. So let's carry on a little bit more here. We have 0 to 2 pi. We have cosine square minus sine square, and cosine square sine, just sine here. And plus sine square t, cosine t, dt. There are two ways you can do this. So either you can split this up into two pieces, and then you take the substitution rule to get the integration of this one and integration of this part. Well, let's take that way. So we have minus of 0 to 2 pi cosine squared t sine t dt plus 0 to 2 pi sine t cosine t dt. And for the first integration, I can just simply find the antiderivative. I think it's cosine cube t minus, so there's no minus anymore. So then I get this by taking the derivative of cosine cube, I get this integrand, right? So I get to 0 to 2 pi. And here I can get it by sine cube t 0 to 2 pi, right? So either case I get 0. So I get 0 and 0. So I know that it's 0. That's one way. So I went through this inner product situation in order to get this, but I can say that I can get right here from this notation. Why? Because I know that x is cosine x, and it's t, y is sine t. So what is dx? So I know that dx over dt is minus t minus sine t, right? So therefore, so this is something that's similar to what you learned in the engineering mathematics 1 in the previous semester. When you, what was it, something like a total differentiation. That's the one technique you can solve it using total differentiation. So you can just split dx and dt as if they are a separate thing, that's some kind of number. So you can say dx is equals to minus sine t dt. So therefore, you can replace dx by minus sine t dt and dy by the same, with a similar argument, we can say this is cosine t dt. Then what you get is after replacing x and y by these two, you get this directly from here to here. You can get this, right? You can just combine dt at the end. You get that. So and then also you replace your information about c by the range of t. Make sense? So that's why I think it's useful. The second notation is quite useful than this first one. All right, so let's look at the example. That's the last one, right? That's 22. So example says the function is two-dimensional function and defined on the right half of two-dimensional plane. So x is positive part. Find the line integration of gradient vector field along the curve C for minus 1 to t from 1t. So basically, it's L1 we just did. So t is changing from minus 1 to 1, and then we want to take the line integration. So here, so we have a vector field f, which is the gradient vector field of that function. So gradient of arctangent y over x. And let's try to get what that is, because it's easy to compute the partial derivative. So first you take the partial derivative of this function in terms of x, delta x, of tangent inverse y over x. and the next one here. And what you get is when you take the arctangent derivative, we had 1 over 1 plus something inside the tangent inverse. So we have 1 over 1 plus y over x squared. And then you have to take the partial derivative of inside. The y over x must have a partial derivative too. So we have a minus y over x squared. And then that's the first coordinate. Let's leave the second coordinate here. And when you multiply these two, let's say you have a minus y on top, minus y. And you want to multiply x squared on the bottom here, x squared plus y squared over x squared times x squared, so it's y squared. So x squared plus y squared. That's your first coordinate. And if you do the same thing for the partial derivative of y, you get x over x squared plus y squared. That's the same vector field we just saw in a previous example. So in this example, we're assuming, so be careful when you define a function. So this function, it says it's only defined on the right half of the plane. So when x is 0, it's not defined, right? But in the right half, there's not going to be any point has x equals to 0. So that's fine. So the function is well defined. And therefore, the vector field is also defined on this domain. Okay? Even though this vector field formula could be defined on the left half of the plane, we're not saying that this vector field can be computed on the left half because that's not the domain of the function. So whenever you get the gradient vector field from the given real valued function, you have to preserve the same domain of the original function. So therefore, the curve must also be lying on the right half of the plane. So I can show you the picture here. So you have x equals to 1 and y from 0 to minus 1 to 1. So in this direction, that's your curve. And so that's because we have a... So if I have to be more rigorous, then I should say more about this curve because the sheer information that t from minus 1 to 1 doesn't imply which direction the point is moving along this line, but let's assume that it's moving upward. Okay, so what is integration of the gradient vector field all along this curve C? See here, ds. So again, I want to use dx dy notation. So in this case, we have minus y x squared plus y squared dx, x over x squared plus y squared dy, and then let's call it c here. X is always 1, right? When I'm moving along this c. There's only one thing moving, one thing that changes, y. The y coordinate is moving. So in other words, I can parameterize this as 1 comma t, okay? So in t is the parameter, so minus 1 to 1. And dx is not, dx is 0, so only preserve dy here. So x is 1 and y is t, so 1 plus t squared, and dy. So y equals to t, therefore dy is dt. So it's tangent inverse t minus 1 to 1. So pi over 4 minus pi over 4 is pi over 2. So later we'll see that this pi over 2 is actually the increment of the angle from the starting point to the end point. So this is pi over 2. So since it's moving upward, if you just measure the angle of the starting point to the end point, it must have been increasing to the counterclockwise by pi over 2. So this pi over 2 actually is where it came from. Okay. So can we move on to the surface integral? This is also overlapping to our previous lecture, so many parts gonna be just review. So let's talk about surface integrations. So there are two types of surface integration again. So surface integration of real valued function and surface integration of vector valued function. So we're talking about the real valued function here. So we have a value of function multiplied with a norm of cross product, which means that it's the length area of a small region on a surface. And we sum them up. So what do you get? So basically it's some kind of a volume because you're multiplying a height with the area, but it's hard to think about the volume element in this picture. So usually what we say about this surface integration is it's a kind of a mass of a surface when we consider F to be the density, point density of that point on the surface. So here, let me give you a meaning with more with a pictorial explanation here. So you might wonder, okay, so we can understand why we need the norm of C prime in the line integration, but sometimes we wonder why this term is required in the surface integration computation. So this is the area, this is actually the area of the parallelogram spanned by the two vectors SU and SV. That's it. So if you take the SU, SV, that's a vector we defined in the previous lecture. So we have three coordinates of parameterization, and we have two parameters, U and V. If you take the partial derivative as of this function, then if you take, say we take the partial derivative in terms of U, then we have xu, yu, zu. So it becomes the three-dimensional vector of that coordinate function. And same for SV. So we have two vectors, SU and SV. Take the cross product. That's just, and you take the norm of that cross product. It is the parallelogram area spanned by these two vectors. But the thing is, we don't want the SU and SV. We don't want actual SU and SV. So here, I'll explain with more picture here. I mean, that's the same picture, but I just want to add more. So our parameter UV sits inside in a different space, in UV space, which is on the left. And S, the parameterization, is mapping my UV point to XYZ point, X, Y, Z. So if I move along these two directions, there's some, so because the point is always moving on the surface, so if I just start to move in this direction, there is a three-dimensional vector that is giving us information about how this three-dimensional point corresponding to this two-dimensional point is just about to move, and same for this vertical movement. Now, I'm not moving actually one unit of, so whenever I move, I'm thinking about moving in one unit of speed, but I'm not actually moving in one unit of length, right? So I want to move it just small bit to the right and just small bit to the top. Okay, so my SUSV is approximate change of my position when I'm moving my point in UV plane by one unit of length. But since I'm moving in small amount, let's say delta U to the right, delta V to the top, what I actually observe as a movement in 3 dimensions is the scaled version of my vector. So SU times delta U is approximately the amount of the actual movement of the point when I move my point in UV plane. And same for this. So I want to take the area of these parallelograms spanned by two vectors. So that's here, SU delta U cross SV delta V. And I want to take the norm to get the area of a parallelogram. But here, these two are just the scalar numbers. So if I have a scalar number, I can always take it out. So therefore, this becomes SU cross SV delta U delta V. So this is actually the small area of each parallelogram spanned by small vectors corresponds to the small movement on UV plane. So why do I need this? Because I'm integrating over the surface, which means that I want to multiply the area of a surface with the value of the function on any part of the surface, right? But how do the problem is, how do I get the area of a surface? Because surface is not flat. If it's flat, it's fine, but we are talking about the round surface. The only way I can get the area is approximate the small portion of the surface, which is round, by the flat parallelogram area. So here, there's a flat parallelogram. The actual area that is correspond to this parallelogram is very round, and it's actually not the same area. It's not even overlapping at all, except for the starting point here. There's only one point overlapping usually. They're not even close. However, if we do that for smaller and smaller area or larger and larger subdivisions, and if we get the limit to be always the same, no matter how we chop the surface off or what direction, if you get the same limit, then we can say this value, the limit value, could tell us something, and this something is called the surface integral. So for example, if I take the value of function to be always be constant 1, just 1 everywhere, then when I take the integration of that constant 1 function over the surface, that's the area of a surface. That is the area. So surface integration is actually defining the area, the very notion, very concept of area of a round surface in 3 dimensions. Without using this integration, the concept of integration, there's no way you can define the area. Even if the surface is like a sphere, a well-known sphere, there's no way without using the integration to get the area. So you see what I'm trying to show you here. So the integration is basically about defining the geometric concept, just like so primitive that we always take it at granted, but it's not always obvious to talk about area of a surface, because we can always, mathematicians likes to do that by making a weird example, counter example that contradicts our intuitions. So intuitively, areas, it's kind of obvious that you have a surface and its area is area. But the question is, there are 2 things. The concept itself is not obvious. And the second thing is, okay, so if you just accept the area is area there, how do you get the number? How do you get the value of that area? The integration of the surface integration answers the both questions. So let's move on here. Oh, so this one, yeah. So we'll get there. So I want to just make a remark. The second example is what we actually done in the classroom. So here, now, before we get to the surface integration of vector field, I want to emphasize that when you do that, you need also take the orientation of surface. You need to provide it by what orientation we're talking about before you compute the surface integration of vector field. So what I didn't explain yet is there are some surfaces that has no orientation. Okay, so here's the summary. So if you classify all the surface, you can classify the surface that has an orientation and the surfaces that has no orientation. So having no orientation means that it is impossible to give an orientation to that surface. So for example, Möbius strip. Everyone knows about this, right? So I haven't heard about this. So if you take the Möbius strip, you cannot tell which side is up or down, because if you run through upside and then come back to the same point, you get to end up with the backside, downside, right? But if you think about the paraboloid or the sphere, there is orientation, and they are the surface that you can put an orientation. For example, there are 2 types of surface also. There are closed surface, which has no end or boundary. There is an open bound, the not closed surface, which has boundary here. So even if it has a boundary, you can tell which side is up and down. So in this case, you can say this is up and this is down. So there are 2 sides of the surface, right? And these 2 sides are not the same. You cannot get to the other side by walking through one side. That's the orientation. If you take the one orientation and you keep the orientation to be your heads up direction, then you're never gonna get to the other side or the opposite orientation by walking along that orientation. But here, again, here's the same. So you cannot get to the opposite orientation. You cannot get to the other side or inside of the sphere by walking on the surface of the sphere. Like if you're walking on the earth, you cannot end up being the opposite side of this earth. What is the orientation now? So we are talking about the surfaces that has orientation, that can be put an orientation on. So orientation is a vector field. Actually, that's a vector field, another vector field, where every vector assigned to each point on a surface is perpendicular to that surface. And there are two conditions. That's the first one, perpendicularity. And the second one is that the norm of vector field is always 1. So how to get the perpendicularity? You can get it by cross product. That's why we need cross product. And we need a normality, so that always the length of the vector is always 1. So you have to divide out by the length of this cross product to ensure that the length is 1. So surface integrals of vector field. This is definition, simple definition. So this is the left-hand side is the notation, and the right-hand side is just the surface integration of real-valued function. So you have a vector field F, inner product with the orientation of the surface N. Okay, so when you take the inner product between two vector fields, you get the scalar function. Okay? So you're just taking the scalar function F inner product N and then integrate. That's all. So also you can define the notion of surface integration in this way. I already mentioned here. And there's one thing. So I want to emphasize. I think I don't have time to explain this in full detail, but I think it's very interesting part. But also, not appears in a most traditional calculus textbook. So if you write your surface integration this way. Each term means that you're projecting your surface onto certain planes. So for example, if you have, so you can split these 3 terms out into 3 surface integration. So this surface integration, and the last surface integration. Let's say we have this surface integration, okay? So this means that basically it has Q and R part equals to 0 in your vector field, doesn't matter anyway. So it means that your surface S is only considered in Y and Z space. What does that mean? So we're only looking at dy dz, which means that I only want to observe the movement or changes in Y and Z coordinates of the point on the surface, which means that you want to look at the surface on top of YZ plane, ignoring the X coordinate movement. And then the only thing that a concern is the Y. So what you look above this YZ plane. And same for other parts. So for example, if you have the last part and integrate the last part only on the surface, then you're looking your surface from XY plane in the parallel direction of Z axis. And then just ignore everything. You want to see how the value of R multiplied with the value of changes of X and Y coordinate and sum them up. So I'll go back to this equation in that sense. So if you have that idea about the surface integral, it's easy to compute the surface integration of that complicated space. All right. So I think I need to talk about the something more. Which I didn't explain before. So if I have to explain in full detail about the Green theorem and the Stokes theorem, then I should talk about this connected and simply connected domain. So here the domain D could be 2-dimensional, 3-dimensional. It's connected if any 2 points can be connected by a curve. Okay? So it's connected. Basically, it's connected right by a curve. And we say that the domain D is simply connected if it's any simple closed curve in the domain can be shrink to a point. So this might seem weird and might confusing why they're using connected and simply connected with the same words connected. And that's basically the mathematicians have devised the word. But so I'll give you the example here. You're looking at the domain D, which is the area between 2 circles, annulus, and this is connected domain. Connected because if you take any 2 points, you can always get the curve inside of domain goes from here to here. And not because you can just connect this through, but because you can go around here and stay always inside of D to connect to the other side. So that's why it's connected. But it's not simply connected. Why? The simply connected means that any loop can be shrink into a point without staying outside, without going outside of the domain. So let's say we're taking a big loop here around this empty circle. You want to shrink it as much as possible into a point. You cannot shrink because if you get to this smallest circle, there's no way you can shrink to one point except jumping around this point, around this hole. You don't want to jump. You want to shrink continuously. So this is not a simply connected domain, but it is connected domain. And one thing that I also want to talk about is the orientation of a boundary. So in the two-dimensional region, orientation is always counterclockwise. But sometimes it's not always counterclockwise. What does that mean? So positive orientation is not always counterclockwise. So if you look at the positive orientation to the surface is the orientation of a boundary where your left hand is always on inside of the region. So if you're looking on the boundary C2 here, if you're moving along this counterclockwise direction with your heads up from this direction, then your left hand is inside your region. But if you're looking at C1, if you're walking on the counterclockwise direction, your left hand is not inside D, it's inside here. You want your left hand side always be your region, okay? So if you want your region to be on your left hand side, you have to walk clockwise direction. So if you think about the positive orientation of your region D, then it's counterclockwise on the outer rim and clockwise on the interior rim, okay? Why is it important? Because it is used in the Green theorem. The Green theorem says that there is a connected domain D, connected, not simply connected, doesn't have to be simply connected, just connected, with a piecewise smooth boundary curve. So there is a curve which is the boundary, but doesn't have to be always one curve. It could be consist of 2 or 3 different disconnected curves. But we want to give the positive orientation to that boundary curve. Just what I explained before. Then these two things are same. That's what Green theorem says. So what is the left-hand side? It's the line integration with an orientation of the boundary, which is the positive orientation to the given region of the vector field. Okay, so these dr, you can just replace as s. And on the right-hand side, what is it? It's just double integration. I mean, there's not even a surface integration. It's just a double integration, okay? Multiple integration, which can be computed by Fubini theorem with iterated integration. But the integrand is not just PQ. It's just PX minus P, QX minus PY, some weird thing going on. So we actually proved this. We proved this for simply connected region, but I'm saying that this can be done with the any connected region. So let's think about this example. I think we can do it right now with our heads. So we have a line integration. We want to find the line integration. How do you find it? The one way is you can parameterize the curve C1, the boundary, which is positive orientation, which in the counterclockwise orientation, by taking 4 parametric curves, C1 to C4, and then just take the 4 different line integration and sum them up. Another way of doing line integration is using Green theorem. So we must be careful about when you use the theorem, whether the conditions are met. So what are the conditions of Green theorem? Let's go back to our statement. So we need D to be connected domain. The region D must be connected domain. Is it connected? Is D connected? Yes, because it's all fully filled. It's not disconnected, right? There is no other chunk of region outside of D. And is the boundary curve piecewise smooth? Piecewise smooth means it consists of smooth parts, smooth pieces. Yes, because the boundary consists of 4 lines. Even though the corner is sharp, which means that it's not differentiable, it can be chopped up into 4 pieces, which are smooth because it's line. And so the last condition is quite a little bit tricky, but let's say in this way. Can we give a positive orientation of the boundary regarding to the domain D? Yes, we can give positive orientation because if we take the counterclockwise orientation of this boundary, then this orientation is positive to D because our left hand is inside of the region when I walk through this counterclockwise orientation. That's the definition of positive orientation. So therefore, I can use the Green theorem. So here we have p y squared and q as x squared. So Green's theorem says that I can get the line integration by double integration of qx minus py. So qx minus py becomes 2x minus 2y, simple function. And then all I need to do is integrate the double integration over domain D on this square box 0, 1. So it's getting really simple, right? You can get it by iterated integral. All right, so this is a proof of Green theorem. I'm gonna skip this. Also, so if you really want to get the exercise, and if you open a book on calculus, and you might see this kind of questions a lot that shows you really complicated integration, and then try to do this, and hoping that you know how to use the Green theorem, and you happens to expect that you somehow remember the Green theorem to use on this example. But this line integration has no meaning. I mean, this example, I made this example just because I just want to show you how the other textbooks are using the Green theorem as a tool to make a line integration easy to compute. So anyway, I can do it afterwards, finishing this slide. So again, this one is already mentioned, the application of Green theorem. So first, this is the Green theorem, and how about this one? So this is just in changing. Oh, sorry. Actually, this is yeah. Sorry. So this is a typo. I'm gonna change the typo before I uploaded it. So this must be minus q dx plus p dy. So therefore, this must be px plus qy dx dy. So in the second equation, what it says is the divergence of the given vector field on the domain D can be computed by this line integration, and this line integration actually gives you the flux across the boundary of the region. So here, so one thing that you can use Green theorem to apply things is that you can get the area of a shape by using the Green theorem. I'm gonna show you. I'm gonna show you when I finish the slide. I need to write something. This one too. This one also I need to explain by words. Okay. So anyway, so before we move on to the exercise, any questions about the Green theorems and surface integration? So let's do the last one first. So how do you get the area of that weird figure? We use the Green theorem. So Green theorem says that if I have a closed curve bounding some region, connected region, then this p dx plus q dy along the boundary can be computed by qx minus py dx dy, right? But what I want when I get the area is I want to integrate just constant one function over the domain. So this is, by definition, the area of the domain. So I want 1 after I computing qx minus py. So one way I can get this is taking qx to be, or making q so that qx to be 1 over 2 and minus py to be also 1 over 2. So if I just add those two, then I get 1. So how do I get 1 over 2 for qx? If my q is 1 over 2x, then I get 1 over 2 for qx. And if my p is minus 1 over 2y, I can also get 1 over 2. So let's define my vector field to be minus 1 over 2y, 1 over 2x, okay? So then what does it say? So if I take the line integration of that vector field along the boundary curve of the positive orientation, then this, whatever that is, will be same as my area bounded by the curve. Okay, let's apply that. So we already have a parameterization, so that's a good thing. So if you take that parameterization, the right-hand side is the boundary of the curve, a boundary of that region, some kind of diamond shape here. So we have 0 to 2 pi of minus 1 over 2y. So what is y? It's the y coordinate of parameterization, which is sine cube. So we have sine cube 1 over 2 cosine cube. And then what? We need to do the line integration. So we need to multiply that with c prime. What is c prime? So first 3 cosine square minus sine t, and 3 sine square cosine t dt. Okay. So let's see, 0 to pi. We have a minus and minus, so it's going to be plus. And we have 3 over 2 common, so let's take them out. And we have sine, so let's abbreviate. So we have sine fourth cosine square plus cosine fourth sine square, right? So therefore I can take 0 to pi. So just combine, make a common factor here, sine square cosine square, sine square cosine square. And the left is sine square plus cosine square, which is 1. So I just need to integrate this. That's not hard at all. So what you want to, so how do you do it? So we have 2 sine 2t square. So if you take the sine cosine, then it's a sine 2t over 2. So it's a squared, so it's squared here. And then we have 3 over 4, 0 to pi. So sine squared 2t, it's 2, 1 minus cosine 4t, right, dt. So this is going to be 0. So, and then this 1 over 2 pi, so it's 3 over 8 pi. Okay? So area is 3 pi over 8. Okay, let's go backward. See which one is interesting. We did this, and okay, let's see. Let's look at this one. So we have a surface, which is, do you see this is kind of the part of a cube, the surface of cube, which is scooped out on the corner here. So it's not sticking up, it's actually scooped out here. So here we have 6 sides, not on the back, only on the part that you see here. There are 6 side surface, and you want to integrate the surface integral. So this surface integrates the integration of vector field, not the real values function. But you can take as if it's just a double integration if you take one by one. So let's look at the first one here. So the integration over S of what? Z, is it? Yeah, Z xy. Z xy. Okay. So you can split into as integration over S1, S2, up to S6. Okay? Because the surface itself consists of these 6 parts. But when you think about surface integration where the parameter is dx dy, you want to find the element of the surface, part of the surface where your area element is non-zero, right? Because if it's 0, if the area element, which is dx dy, is 0, there's no point of integrating because it's always going to be adding 0. So think about S1 here. S1 is sitting up x-axis. Is there xy? Is there any area element in xy dx dy? Dx dy means that you want to see the area projected on the xy plane. What happens when you project S1 on the xy plane? It becomes line. Does line have the area? No. The area element is always 0. So even though the value of z, the function, changes across this S1 boundary, We don't have to integrate. There's nothing to integrate because area element is 0. Same for S6, same for S3, S5. The only part we don't have non-zero area, we don't have zero area is S4 and S2. Because S4, when you project it on XY plane, it's just exactly the same because it's parallel. And same for S2. So everything is 0 except S2 and S4. S2 and S4. So on S2, what do you do? So XY here, it's just same as Y. So XY coordinate of the point on the S4 is exactly same as the XY coordinate in the XY plane. But how about Z? So the Z coordinates of the point on the surface S4 depend on XY coordinate? No, because S4 is just flat surface parallel to XY plane, so it's always what? 1. Z coordinate is always 1 on S4 surface. So here it's just integrating 1 dx dy. And on S4, how about S4? What is the Z coordinate? What is the Z? It's always 2, right? So you're integrating 2 dx dy. By the way, it's not, it's just because the shape of surface is very special. It's flat and it's parallel to XY plane. That's why we have a number 1 and 2 here. If the surface is, having an up and down, then it means that the Z coordinate, the height is depend on XY coordinate. So the integrand must be the formula of X and Y. Anyway, let's finish the computation here. So we are taking S2, but not as a surface on XYZ space, but as a projected surface, projected domain on XY plane, but that's the same thing. It's what? Just square of side 1, side length 1. So basically it's the area of a 1 by 1 square, so it's 1. How about this? So we are taking the surface S4 projecting on XY plane, and that's the same, exactly same thing, and area is 3. So we are taking area 3 multiplied by 2, so we get 6. So therefore, the integration of the first part over the surface S is 7. And you can do the same thing for the other two, these two and these two. Okay, so let's see. Now, how about this one? I think we can do it without using this blackboard. So let's say S be the unit sphere whose orientation is outward. Okay, entire surface sphere, and the orientation is outward. Find the surface integration of this. So there is a vector field. So here is the vector field, vector, and we divide out by this number, just as a scalar multiplication, and then there's a vector field notation. How to get this? So what is the orientation on a unit sphere which is outward? So your orientation is defined on the sphere. So let's say your point on the sphere is x, y, z. Okay? And then if you take the unit sphere in the same direction perpendicular, if you take the unit vector perpendicular to the surface of the sphere, it's the same vector that you make from the origin to that point x, y, z. Because if you just extend your vector from the origin to x, y, z on the unit sphere, that is exactly the unit sphere and it's perpendicular to the sphere, right? Your orientation is x, y, z. Your orientation itself is x, y, z. And if your x, y, z is in the unit sphere, you don't even need to do this, x squared plus y squared plus z squared, because that's already 1, right? It's the distance between the origin to the point on the unit sphere. That's 1 by definition. So it's 1 here. And you have a vector field and the orientation inner product with to get x squared plus y squared plus z squared, which is also 1. So what happens is after you're taking this as normal surface integration of this function, the f times n, this whole thing in the previous example becomes 1, just 1. Okay? You're integrating function 1 over the unit sphere here, in the first example here. What does that mean? you're getting the area of a unit sphere, right? Integrating 1 over the surface, it's the surface area. What's the surface of area of a unit sphere? 4 pi, yeah. So you don't have to even compute. I mean, even if you compute, you get the same answer, but just 4 pi.